Hi everyone, I am SS Kiran. I would like to discuss about classification of systems. Previous video I have discussed transformations like time shifting, time scaling, time inversion. Introduction about systems and definition of system. Okay, some types of systems. In this lecture, in this video, I will be discuss about static and dynamic systems, linear and non-linear systems, causal and non-causal system, time invariant and variant system, stable and unstable system, invertible and inverse system. The last topic, analogy between vectors and signals. Okay, right. We will enter into the topic. Sometimes there is a chance to ask which system is dynamic or stable or static, causality, invertibility. There is a chance to ask in our end examinations and gate examination also. See here, every time you have to concentrate definition and some mathematical expressions. Okay, you will get full clarity, right? Right. Now first we will start with static and dynamic system. Static systems are also called memoryless systems. See here I have underlined static systems are also called memoryless systems. Coming to dynamic systems is also called memory systems. Okay, static systems are called memoryless systems. Dynamic systems are also called memory systems. Right? What definition said? A static or memoryless system is a system which output signal value depends on the present value of the input signal. Please underline this point, present value of the input signal. What it is called? Present value of the input signal. I think you can understand, right? Okay, now example, see some examples how it depends on present value of input signal. See here some mathematical expressions. These examples are combinational logic circuits. Static systems are used in the combinational logic circuits. The first expression is y of t is equal to x square of t. So see here, this is the present value of the input signal. See here, y of n some value or output signal. So here x of t is the input signal. So both time having tt. So this is nothing but present value of the input signal, right? See here some mathematical expressions here mentioned one by one. So y of t is equal to x square of t, and discrete signal y of n is equal to n into x of n. Y of t is equal to 10 into x of t plus 5. Y of n equal to a to the power of n into x of n. These static signals depends on only the present value of the input. Okay, present value of the input. I will show uh, t here, t present value of input, n t here, x of t, y of n. Okay, then this is the x of the n, x of n, right? Now coming to dynamic systems. Dynamic systems are also called memory systems, right? A dynamic or memory system is a system in which output signal depends upon past and future input signal values. Okay, here once again I underline the point, you can understand, right? Past and future input signal values, right? Past and future input signal values, right? Okay, these are the dynamic systems. I will show some mathematical expressions, you can understand. See here, y of t is equal to x of t plus x of t minus 1. This x of t minus 1 is the some future input signal, right? Sorry, past. Okay, past input signal. Okay, these signals past or future. Okay, past or future. See, y of t is equal to x of t minus 1. This is past. Y of n is equal to x of n plus 1. This is the future. The our input signal values, which is depends on past and future input signals. Those signals, those systems is nothing but the dynamic systems. Okay, the next, see some examples. Now some mathematical expression, one more mathematical expression. Y of n equal to sigma k equal to minus infinity to t infinity x of k, right? Then in the continuous waveform, y of t is equal to 1 by c minus integral minus infinity to t x of t of d tau or x of tau d tau. Example for continuous with memory, time system with memory, right? Second one, linear and non-linear system. Okay, in this system the best example is superposition theorem satisfies. Okay, satisfies the superposition theorem. See here closely, you can understand. A system is said to be a linear system if it is satisfied superposition principle. It states that the response to the sum of weighted inputs as same as the sum of weighted response. Weighted inputs, this is the weighted inputs of the sum of the inputs, weighted response and weighted input. Those systems is called the linear systems which is satisfy the superposition principle. Which does not satisfy superposition theorem, those systems is called the non-linear system. See here mathematical expressions you can understand, right? See, I have to underline here, this is the mathematical expression. See, okay, this is the mathematical expression, right? Now then second one, see here, a system which does not satisfy superposition principle is called the non-linear system, right? Just now I have discussed it. See some examples. Check whether the given system are linear or non-linear. Good. Y of t is equal to t into x of t. That is first example. The second example in the discrete form, y of n equal to x of n plus 1 by x of n minus 1. The first, let us start with first example. Y of t is equal to t into x of t. Yes, good. X1 of t and x2 of t be the two input signals. Here two input signals. What are the two input signals? And y1 of t and y2 of t be their corresponding outputs. Let us start with y1 of t equal to t of x1 of t is equal to t into x1 of t. Just simply we can write some mathematical expression for y1 of t. Then second one, y2 of t equal to some transformation of x2 of t into x2 of t. Weighted sum of the outputs or sum of the weighted responses. See here, just simply I can add these two expressions, a1 y1 of t plus a2 y2 of t. Then what about these functions a1 into, see here mathematical expression, you can understand, a1 y1 of t, a2 y2 of t and is equal to a1 of, okay, this is the mathematical expression, right? Underline here, right? Then what happened, the equation a1 into t of x1 of t and plus a2 of, substitute, write the equation from this one, okay, right? So satisfies the superposition theorem, those systems is called the linear systems. It does not satisfy the superposition theorem, those systems is called the non-linear system. So finally 1 and 2 is equal, that's why it is called superposition principle satisfied, hence the system is called the linear. Coming to second expression, y of n is equal to x of n plus 1 by x of n minus 1. See, same mathematical calculation we can substitute here. See here closely, you can understand, right? Okay, now weighted sum of the outputs is given by like that. So same mathematical calculations applied here. Finally output due to weighted sum of the inputs due to see here that does not matches with first equation to second equation, which does not satisfy the superposition theorem. That's why those equations is called non-linear systems. Okay, see here the example, you can understand. Okay, the first expression how got a1 into x1 of 1 plus a1 by x1 of n minus 1, here a2 by x2 n minus 1. What we get here is this expression is not equal to the first expression, that's why it is not satisfied the superposition theorem. If it is not superposition theorem, so the system is called the non-linear system. Yes, third one, causality. Okay, or causal system or non-causal system. A system is said to be a causal system if the output of the system at any time, very important, any time depends on the present and past inputs. See here, underline what, present and past inputs. Okay, present and past inputs, but does not depend on the future inputs. Those systems is nothing but the causal systems. Okay, I will tell you once again, A system is said to be a causal system if the output of the system at any time depends only on the present and past inputs but does not depend on the future inputs. If the output of a system depends on future inputs, then the system is said to be a non-causal system or anti-causal system or anticipatory systems. Okay, this does not the output of the system depends on only future inputs. Coming to the causality, depends on only the present and past inputs. It is, and coming to non-causality, depends on the future inputs. I think you understand the variations, right? Those non-causality systems is also called anti-causal and anticipatory. Now we will see some examples. See the some mathematical expressions you can understand. Causal systems and non-causality systems. Okay, y of n equal to x of n plus x of n minus 1. Y of 2 is equal to 2 into x n minus 5 of minus x of n. These systems are called the causal systems. Okay, present and past inputs are depend here in the causal system. Is said to be coming to non-causal system depends on the future inputs. See, I will show the some mathematical form. See here, y of n. Okay, by x of n minus 1. X of n is the present and past inputs. Okay, here non-causal system, it depends upon only the future inputs like 2n 2 plus 3. Okay, right. Now in any practical systems, the output at any instant depends on only on the present and past inputs. It is not possible to build a practical system. Yes, some theoretical matter. See some examples. You can understand the which system is called causal and non-causal. For first one, y of t is equal to x of minus t. This is first example. So y of t is equal to x of minus t. Take some different values. T equal to minus 2, t equal to minus 1, t equal to 0, t equal to 1, t equal to 2. If t equal to minus 2, we get x of minus 2 is equal to x of 2. Okay, see here, this the output y of minus 2 depends on the future input, that is called x of 2. So the system is called non-causal system. See here, y of minus 2 depends on the future input. What definition said? The system depends on the future inputs, then the system is said to be a non-causal. Same operation happened here. Okay, hence the output y of minus 2 depends on the future input, that is called x of t. So the system is said to be a non-causal system. Okay, see the second example. This is also said to be a non-causality of the system. Okay, see third example. Just I have in my description I have provided my notes. Okay, just to go through it, you can understand, right? Okay, time invariant and time variant systems, very important. A system is said to be a time invariant. Okay, a system is said to be a time invariant or shift invariant if the characteristics of behavior of the system do not change with the time. Okay, system is said to be a time invariant or shift invariant if the characteristics of behavior of the system do not change with time. Those systems is nothing but the time invariant systems. Okay, for a time invariant systems, if y of t is the output of the system, see here closely, for a time invariant system is y of t in the output of the system to the input x of t. Of x of t is delayed by t1 seconds, the response y of t should also be delayed by t seconds. Those systems is nothing but the time invariant systems. See the mathematical expression, x of t minus t1 tends to y of t minus t1 or y of t minus t1 is equal to transformation of x of t minus t1. Those systems is called the time invariant systems. Now coming to time invariant system. A system is said to be a time variant system or shift variant system if the behavior of the system, input output characteristics of the system changes with the time. I think it's a word having the meaning that is called time invariant, means with change in the time. Time variant means with the system changes with the time. Okay, the time invariant means does not change with the time, it is change with the time for time variant systems. Time is vary here or shift, right? Now see some examples, you can understand. The first expression, first of all, example, determine the time, the following systems are time variant or time invariant. The first one, y of t is equal to x of t not equal to x of t minus 1. Okay, y of n is equal to x of minus 1. See the first one, y of t equal to transformation of x of t, then x of t is equal to x of t minus 1. If the input delayed by k units, simply you can write some mathematical expression, t of transformation of x of t minus k delayed by k unit, and this is also changed, x of t minus k plus x of t minus k minus 1. See here I have underlined, you can understand, right? See this one, this is the expression 1, this is the output delayed by k unit, this is the expression 2. The finally 1 equal to 2, so this is the system is nothing but the time invariant system, right? If 1 is not equal to 2, those systems are called the time variant systems, right? Okay, next we will see the next example. Y of n is equal to x of minus n. So in this, you do some mathematical expressions, we will get the some final value. 1 not equal to 2, so that's why those systems is nothing but the time variant systems. Okay, just see the closely, you can understand, right? Now the fifth one, stable and unstable system. A stable system is said to be a stable if the produces bounded output for bounded input. It's satisfy the Bibo concept. Okay, which does not satisfies the Bibo concept, those systems is nothing but the unstable system. Which is that satisfies the Bibo, bounded input, bounded output, those systems is nothing but the stable system. Which does not satisfy the Bibo's concept, bounded input, bounded output, those systems is called the unstable system. Stable system, the equation is, see here, stable system, you can understand, stable system, this is the condition. Okay, this is the condition. Okay, for a stable system the input must be bounded, x of t less than infinity, mod x of t less than for all values of t. Okay, y of t less than 8 for must be bounded. Okay, the input is must be bounded and output is also must be bounded. Those systems is nothing but the stable systems. Coming to unstable, a system is said to be unstable, condition is not satisfied. See here, see closely, condition does not satisfy, those systems is nothing but the unstable system, right? Now example, find whether the system is stable or not stable. Y of n equal to 1 by 2 all to the power of n u of n. See, you can write mathematical expression, already I have shown here, sigma n equal to minus infinity infinity 1 by n all to the power of n u of n. So do some mathematical calculation. Okay, so like that, 1 plus a square plus a to the power of 3 infinity, we get the formula for 1 by 1 minus a. Okay, now the phi of n is equal to 1 by 1 minus 1 by 2 equal to 2, so 2 less than infinity, so the system is stable, right? Based on this concept, we will conclude the system is the stable. Now sixth one, invertible and inverse systems. A system is said to be invertible system if there is one-to-one correspondence between its input and output signals. Okay, very important. A system is said to be a invertible system if there is one-to-one correspondence between its input and output signals. One-to-one. So I think you can see some example, you can understand, right? If system is invertible, then an inverse system exists. Okay, invertible and inverse system. If a system is invertible, then an inverse system exists. Example, y of t is equal to 2 into x of t. Its inverse, x of t is equal to 1 by 2 into y of 2. So another example of invertible system is accumulator. Accumulator is the good example for the invertible and inverse system. Okay, now its inverse, right? For lossless coding, the input to the encoder must be exactly recoverable from the output. Yes, absolutely. It means that the encoder must be invertible. Okay, good. The cascading of invertible system and its inverse system is equivalent to the identity system. See here, this is the invertible system. Y of t is equal to 3 into x of t. What about inverse system? X of t is equal to 1 by 3 into y of t. So finally we get the output. Whatever we can give the input x of t, the finally we get the x of t is the output. These systems we can use the encoding and decoding in the communication side. we can use in the communications side. So one is the invertible and another one is the inverse system. Invertible system, the mathematical expression is y of t is equal to 3 into x of t. X of t is equal to 1 by 3 into y of t, right? These are all the systems. Okay, now see some analogy between vectors and signals. I think there is no need of these are all mathematical expressions, mathematical calculation. Simply you can concentrate the formula. That is more than enough. If there is a doubt, here in description I have provided my notes. Just you go through it. Simply you can observe. Definitely you can understand. If you cannot any understand, just you can discuss in the comment section. Okay, right, sure. Now what is orthogonal? You know, orthogonal, 0 if both are perpendicular, so we can also call as orthogonal vectors. Okay, these are already we discussed in the lower sections also, right? Just you can concentrate only the equation. Okay, that is more than enough, right? The first one, the two functions f1 of t and f2 of t are orthogonal over interval, so we can write like this. Okay, integral t1 to t2 f1 of t into f2 of t with respect d2 equal to 0 if it is orthogonal. If it is not orthogonal, so write the constant c12 equal to this mathematical expression. Okay, t1 to t2 f1 of into f2 of t dt. Okay, by integral t1 to t2 f2 square to dt. If it is orthogonal, this is the final expression. Just this is enough to remember this equation. Why? Because we are only doing the problems. Okay, that's why just you can remember this formula for orthogonality of the two functions or two signals or two systems. Simply we can write t1 to t2 integral t1 to t2 f1 of t into f2 of 2 with respect dt equal to 0. Those systems are said to be a orthogonal. Thank you. Just in my description I provided my previous lectures. Okay, just to go through it, you can understand. I have provided my notes also. Okay, thank you so much. Thank you.